Well, thanks very much, Eric, and to the organizers of the conference. It's wonderful to be back in the Northwest. I think a lot of you probably take for granted what it's like to take a shower without feeling guilty. Although I think after hearing Amy and John talk, maybe that's not going to remain the case. So I was asked by the organizers to talk a little bit about where we're headed in terms of the climate futures there's a wide range spanned by the RCPs that Dennis introduced earlier, and where we might be headed within that range. And so I think as a preface to my remarks, despite my cheeky title, Possible But Likely, I think it's important to point out that I obviously don't have a crystal ball and I don't know what's coming in the future. But what I will do is show you what is entailed in terms of the relationship of energy, emissions, and economic growth in the different RCPs, and then compare that with some recent trends in the data of what's actually happening. And I'll do my best to let you sort of read into that what you will and draw your own conclusions. And then towards the end of my time today, I'll talk a little bit about some work I've been doing on what I call committed emissions, and I'll tell you more about that when we get there. So backing up for a second, let me move this up. In case any of you aren't intimately familiar with the RCPs, it does stand for Representative Concentration Pathways. And in essence, they're the new scenarios that the IPCC has adopted as a framework for doing all sorts of analyses of mitigation, impacts analyses, and adaptation work. So on the left-hand side here, what you're seeing is the radiative forcing this century under these 4 different RCPs. And the numbers after each RCP refer to the watts per square meter of forcing that each one entails in the year 2100. And because in each case these have been realized as emission scenarios where CO2 is the dominant driver of that radiative forcing, you see that on the right-hand side, CO2 concentrations in the different pathways also diverge widely with, say, RCP 2.6, the green line there, peaking. Did this thing just go off? I don't know if maybe the battery or something. Can you hear me? No?
All right.
I could try to use the podium if you want.
Let's try the handheld for now.
Well, that'll make me feel like an MC. That'll be great.
This is test, test, test. Test, test, test. Yeah, it is. This is a new one that they brought to deal with the static.
The saga continues. Seems like none of them are working.
Yeah. I'm sorry about this.
It's okay, I'll go fast.
No, you're fine. Don't worry about it. All right, test, test. Okay. Well, we've got this one. All right, go ahead and just use that one.
Okay. So as I was saying, on the right-hand side here, we see the CO2 concentration in the atmosphere under the 4 different RCPs. And the green line, the lowest RCP 2.6, peaks at around 450 ppm and then declines in the end of the century. And on the other end of the spectrum, you see RCP 8.5 just off to the races, and it's up around 900, 950 ppm in the atmosphere by the end of the century. So obviously there's a big difference here, and the integrated assessment modeling community, the folks who kind of look at what energy and emissions are going to be to make these different pathways, have really never wanted to assign any probabilities or tell us which of these may be more or less likely. And that's just because they're committed to the idea that scenarios are not predictions of the future, they're just possible futures. But I'm going to try to break that today because I'm not an integrated assessment modeler. And so this is a plot that Dennis showed earlier, and he described it as complicated, which I think he's right about that, but hopefully his explanation and mine together will amount to you understanding it. What it's showing you on the x-axis is the cumulative CO2 emissions since the year 1870, so essentially pre-industrial era. And on the y-axis, the temperature anomaly, the warming relative to the same time period. And as he pointed out, the different RCPs are plotted on here, and they all fall along basically a line. Give or take some uncertainty in the climate models, you can see, though, that different cumulative emissions under these RCPs lead to different degrees of warming. And so for a rule of thumb shorthand, you could think of RCP 2.6 as the one that is likely to avoid 2 degrees of warming relative to the pre-industrial. RCP 4.5 is likely to avoid 3 degrees of warming, RCP 6 likely to avoid 4 degrees, and RCP 8.5 goes beyond 4 degrees and up towards 5 degrees by the end of the century. And the reason I like to look at this cumulative framework is that what I've done here on the bottom is plotted a bar chart of the known proven fossil fuel reserves around the world on the same axis. And you can see that all except for RCP 8.5, all of these are within the range of the known economic, accessible fossil fuels that we have. A big chunk of that is coal, but as one of the previous speakers mentioned, we are constantly expanding these known reserves, and so oil and gas companies are out every year exploring and adding to this stack of fuels available. And you can see that on the end there, there's the unconventional oil and gas, things like fracking have led to be economic. So the point here is that we actually need to think of this something like a cookie jar. The fossil fuels are like cookies in a jar, and they're attractive and they're tempting, but we and our ancestors have to keep our hands out of that jar if we're going to have any hope of stabilizing the climate at a reasonable temperature from now until the end of time. So that's a little bit daunting. But that's going to be hard because at this point, we still derive the lion's share of our energy from fossil fuels. This is just a simple pie chart that in 2010, around 84% of global energy used came from coal, oil, and gas, with the remainder made up 6% of nuclear and 10% renewable. And so lest any of you in the audience are sitting there thinking that renewable is really fancy solar panels, I should say that most of that is hydro and biomass, with a very small part of that green slice, small but growing, represented by solar and wind. So not only are we depending on these fossil fuels for a lot of our energy, but this is a plot showing you what energy supply, or you could think of this as energy use, does in all of the RCPs over the 21st century. And you can see that, especially since that vertical axis is logarithmic, there's strong growth that we're going to see in energy use in all of the RCPs. So for instance, even in RCP 2.6, the sort of low warming world, we see a 50% increase in energy use around the world by 2050. RCP 6 grows by 80% relative to the 2005 time period. And the highest RCP 8.5 is more than doubling of energy use by the middle of this century. And so this has to do with a little bit population growth, but more the actual accessibility of energy services as places in the developing world develop economically and people start using more energy in those areas. The range, I should say, among the RCPs has a lot to do with not just the economic growth of those areas, but how much energy we should assume is required to grow the economy in those. And so in some of these scenarios, the models tell us that energy might be used more efficiently. So for instance, with service industries rather than really energy-intensive industries like making steel and cement and so forth. So the point here is that energy is expected to grow, and in reality, is what I'm plotting here in red, you can see that there has been significant growth in energy use going back to 1985. And in reality, funny enough, the energy that's being used is actually above where RCP 8.5, above the upper bound of the IPCC's scenarios, ever since their inception back in 2005 is when they have their first data point there. Okay, so what I was saying is that in reality, we're actually already above the envelope of these RCPs in terms of energy use worldwide. You can see a tiny blip there in the reality, which corresponds with the global economic recession. But growth is along the lines of RCP 8.5 or above. Turning to what emissions look like in the different RCPs, there's a very broad range, as you'd expect, of what annual CO2 emissions do over the 21st century among these RCPs. And so on the bottom end, RCP 2.6 would require us to basically have flat emissions for the next 20 years, then drop sharply and actually get into global net negative emissions toward the end of the 21st century, which I think a lot of us have trouble believing that that's possible. It has to do with the models are implementing biomass energy with carbon capture and storage. So there's actually, in theory, an ability to draw down CO2 from the atmosphere, and I think that came up with one of the previous questions. On the upper end, you can see, again, RCP 8.5 is just soaring and actually reaches 5 times the current level of CO2 emissions from fossil fuels by the end of the century, so close to 150 billion tons of CO2 a year. In reality, you can see that we've been increasing ever since 1980 here, and there's actually kind of a crook in that observed data around 2001, which has to do with the rapid industrialization of China and the fact that they're fueling that industrialization with really carbon-intensive coal. And so we've been following along, as I think Dennis intimated, this really high emissions pathway of RCP 8.5. And we're a far cry from stabilizing emissions. These things are growing year after year. So about 3% a year, in fact. So combining these two, energy use and carbon emissions, you can look at an interesting and useful metric of the global energy system, which is the carbon intensity of energy. How much CO2 are we emitting for every unit of energy here, plotted gram CO2 per megajoule that we're using? And so this is really telling us something about the energy mix and how much of that mix is made up of fossil fuels. So the only one of the 4 RCPs that increases in terms of carbon intensity of energy is RCP 8.5, and that's because it anticipates an increase in the amount of coal that we're burning for energy relative to the present. The other 3 all drop, and again, you can see the RCP 2.6 actually gets into the zone of negative emissions per unit of energy. Again, this is sort of that BECS, the biomass with carbon capture and storage. So how does reality compare here? Well, we actually see that we had a long-term decline in carbon intensity of energy from 1980 to around 2000, but that reversed, again to do with rapid economic growth in the developing world, and particularly China, and the fact that they're fueling that with coal. So since 2000, 2001, we've actually been increasing in the carbon intensity of energy worldwide. So that's obviously a negative thing, and it certainly resembles RCP 8.5 more than the others. Again, you see that little dip sort of towards the end of that reality plot, and that's to do with the global economic recession, which temporarily put us on track for RCP 4.5, but we've bounced back. So the last one of these kind of series that I'll show you is what renewable energy is supposed to do under the different RCPs. So here you see these are reversed, where you get the most renewable energy in the future under those low warming scenarios of RCP 2.6 and rather less in the warm world of RCP 8.5. But growth, and pretty important growth, in all of these RCPs. So in reality, we are growing the amount of renewable energy that we have worldwide, and you can see, again, kind of a crook there around 2001, where we've taken a new trajectory, growing that renewable energy supply faster than before. Unfortunately, we're still sort of just a hair above where RCP 8.5 would have us in terms of renewable energy, not quite up to the RCP 6. So we're increasing this renewable energy that we have, but not enough yet to avoid 4 degrees of warming. And so, you know, obviously, I think one of my colleagues puts this nicely. The green horse, if you will, being renewable energies, is running faster than it's ever run. The problem is that the brown horse, which is fossil fuels, is many, many lengths ahead, and it's not slowing down. So, one final way of kind of thinking about the RCPs is what's called decarbonization. And so by decarbonization, what I'm talking about is emissions per unit of GDP. This really ties together the emissions and the economic growth. And what you see is that in the different RCPs, RCP 2.6 in blue on the left implies that we decrease the emissions per dollar of GDP on the order of 4.5% per year in the first half of the century. More modest decarbonization under RCP 4.5 and 6 is somewhere between 1.5 and 2% decarbonization every year, and RCP 8.5 is down there with the very seemingly attainable 0.5% decarbonization a year. And so since economies are usually expected or at least desired to grow at a rate of maybe 2 or 3% a year, this means that we'd need, under RCP 2.6, for instance, an absolute reduction in emissions on the order of 6.5 or 7% a year, which seems a very tall order considering that we're growing gangbusters now and we're only increasing it at 3% a year. We need to go at least twice as fast in the other direction. So observations here, in the 25-year period between 1985 and 2010, the global economy decarbonized at a rate of about 0.8% a year. So not terrible, but closer to RCP 8.5 than 6. And in the decade between 2000 and 2010, we've actually seen a recarbonization, again to do with increased coal use in China mostly, by about 0.5% a year. So we're literally going in the wrong direction here. Now, I think no one who's been in this room and seen me present these trends that are existing in the data would say these are anything less than sobering, but I think that the past is only so good a guide to what the future holds. And so some work that I've been doing looks at a different way of predicting what might happen in the future, and it's what I call committed emissions. And it has to do with the fact that fossil infrastructure tends to be very long-lived and is a very expensive proposition that can tell us something about what we might expect in the future. So if you stop to think about it, we've spent 200 years and literally tens of trillions of dollars building what is the largest network of infrastructure that's ever existed on the planet. Things like pipelines and shipping terminals, and pump jacks and power plants. So the idea is this stuff presents us with some inertia, and the existing infrastructure tells us something about what we can expect for future emissions. So what I did to try and assess this was I modeled the hypothetical that we stop building anything that burns fossil fuels today. So we never build another power plant or car or lawnmower or furnace, but all the ones already in existence live out their expected lifetime. And I used sort of historical lifetimes for that. And what you're seeing here is a wedge of emissions out into the future as all of these existing devices live out those expected lifetimes and are retired. And so the big red one on the bottom is the power plants, the primary energy sector. And the punchline here is that over the next 40 years, we actually ramp down to near zero in terms of this energy infrastructure. And cumulatively, this represents around 500 billion tons of CO2, at least as of 2009 when I did this study. So I think if you overlay that with what annual emissions look like in the different RCPs, you can see that it's quite significant relative to something like RCP 2.6. It really doesn't leave us a lot of breathing room to hit that kind of a low target. It's less significant in an RCP 8.5 world, but that does imply that we're going to be building a lot of new infrastructure to follow that high emissions path. So, you know, I say this committed emissions analysis is both good news and bad news. The good news is existing devices probably aren't going to put us over climate thresholds like 2 degrees. We're going to have to build new things to get past that. And that means that it's still possible to turn the ship. This is some climate model output of if you fed that 500 billion tons of CO2 into the climate model, you see that we actually stabilize the global mean temperatures at around 1.5 degrees by 2060. So this means that if we decided today to stop building power plants and start building only solar panels and wind turbines, we could stop this problem from hitting the 2 degree mark. Of course, the problem is, and this is the bad news part of it, that's not really what we're doing, and that's a pretty drastic assumption, obviously. I do think that what we do now is very critical. So this is the same wedge of existing infrastructure's emissions into the future, but here, instead of being broken out by the type of infrastructure, it's divided by where that infrastructure exists. And so you see in the purples at the bottom, the very young energy infrastructure that exists in places like China and India. Those things are flat for the next 20 years. Those aren't going anywhere. In contrast, in green and the light blue are Europe and US emissions, and you can see that those things drop very sharply in the next 5 to 10 years. And that has to do with the fact that a lot of the infrastructure in these countries is nearing its expected age of retirement. And I think that presents a real opportunity for us to get behind building the right kinds of energy infrastructure and not doubling down on the pre-existing fossil infrastructure. So following up on this is a paper that I just had come out a couple weeks ago with a colleague of mine, Rob Sokolow. We've looked back in time and seen how has the total committed emissions relative to power plants increased over time. So this is showing you how those total commitments have grown from near zero in 1950 to a whopping 307 billion tons of future committed emissions from power plants worldwide in 2012. And the colors on here showing you where these power plants are. So that huge ramp up of red is China, and you can see that right now 42% of that 307 are power plants in China. So this is the problem. It may be possible to turn the ship, but at least according to this, these commitments are growing at a rate of about 4% a year, even faster than annual emissions, which means that the ship is proceeding full speed ahead. So the last thing that I'll talk about is some work that kind of rolls a lot of this up together. The fact that warming will be proportional to cumulative CO2 emissions means that you could define a quota of how much emissions we have available to us as a globe in order to hit a specific climate target. And so I've been working on a paper that's in press now that combines what's happened in the past, the cumulative emissions in the past, which is the purple bar on here, the 1.3 trillion tons of CO2, with the current global commitment from all energy infrastructure in the orange bar, around 700 billion tons now. And then in the three green shades shows us what our quotas are for hitting a 2 degree, 2.5 degree, or 3 degree target going forward. And again, I've plotted over top the known fossil reserves that exist today and how that stacks up. So you can see we have plenty to get us to a 3 degree range. What's interesting is not only can you define this quota, but you can then start playing with quantitative methods of how to divvy up that quota among nations, which has really been the showstopper for collective action on the issue of climate change and how to mitigate these emissions. So in North America, what I've shown here is 3 options of how to share emissions among nations. The inertia bars on there are reflecting the current distribution of emissions worldwide. So kind of keeping on with the developing countries like China, as well as developed regions like the US, Europe, and Japan, getting most of the emissions share. Whereas the equity bar at the bottom would divvy up the remaining quota on a per capita basis worldwide. And the middle bar, the blended, is kind of a hybrid of the two, a 50-50 split. And so the point of this is that, you know, we could imagine that the nations could get behind some sort of a blended approach where you'd kind of split the difference between the countries who are going to have to phase out their energy infrastructure very rapidly, as well as all those countries that want a piece of that remaining pie so they can develop, and that would be sort of the equity angle. And you can see that there's a very specific number on here, 72 billion tons of CO2 that North America would have under this blended scenario in order to hit a 2 degree target beyond the current commitments. So the idea here is that this might have some help in the international negotiations, but it's really getting down to we have a runway if we want to hit a specific climate target. Depending on what that target is how long the runway is. But with the past emissions and the committed emissions, we know how far down that runway we already are. And so we, in this country, have somewhere between 26 and 50 years of emissions at current levels if we wanted to hit a 2-degree target. And you can do the same sort of exercise with China and other countries. So just a few wrap-up points. I've shown you that all of the RCPs anticipate really substantial growth in energy demand over the century as especially developing countries get access to energy and grow. All the RCPs, though, differ very widely in the extent to which that demand is going to be met by fossil fuels. And unfortunately, I showed you that actual emissions and the trend in the carbon intensity of energy are following the worst-case RCP 8.5 path. So although it's theoretically possible that we could get off of that path and jump down with a huge political will, that would mean fighting substantial inertia in the fossil energy system, retiring these power plants and things early or retrofitting them with expensive carbon capture and storage technology, for instance. And so, unfortunately as well, the inertia in the system, those committed emissions I showed you, are still growing. We've actually built more coal-fired power plants in the past decade than in any previous decade. So we're not stopping this. We're actually doubling down. So there are some positive signs. I don't want to be a complete downer. The global picture is not great, but locally and in certain regions, for instance, it's been brought up that emissions are down in the US. Our commitments based on the infrastructure we're building are also down. And renewable energy globally is growing faster than it's ever grown. So these are all positive signs, but unfortunately, they don't yet add up to being anything less than that worst case path. So given all this, I think it's the case that RCP 8.5, that high path, seems considerably more likely than RCP 4.5. And at least to me, RCP 2.6 seems completely implausible. And so I think for the community of folks that I'm addressing here that are doing impacts and adaptation analyses, it's important that we don't let our scientific conservatism have us choosing the middle of the road pathway only to look at, as some of the plots Amy showed. We should be willing to at least entertain the fact that we're headed down the high emissions path and make sure we also look at what the future holds on that path. So with that, I thank you and I take some questions.
Test, test, test. Okay, our experiment with audio will continue as we do the Q&A. We're going to hand this, I'm going to hand this to you, Steve, and we're going to then daringly turn on the handhelds and see if Steve combusts like Spinal Tap.
Did you turn it to 11 or? Yeah. Okay.
There was a request from someone in the audience. If you could please state your name as you say your question. That way, if anybody thinks your question is particularly interesting and wants to follow up with you, they can find you in the crowd. There is a question way back there. So if you could just wait for the microphone to get to you. Can you go up with guys? I can talk loudly.
If I recall from one slide earlier in your presentation, my name is Ted Wilson. I'm from Fort Valley.
Hey, Ted.
Several times you mentioned that China is building coal-fired power plants. India looked like it was making a relatively small contribution to the coal economy. Maybe I got that wrong. It was a very thin wedge on one of those slides. What's going on with India?
Well, India is building a lot of coal, but they haven't industrialized in the same way that China has. As you probably know, they've gone down more of a tech path with some of their development, so they have a less energy-intensive economy. But they actually represent current commitments of power plants in India that I quantified are almost the same as in the US and Europe. So it's a big piece. It's just dwarfed by the massive build-out of coal power in China.
Any other questions? Raise your hand so we can go in here.
I'm Katie Kruger. I work for a tribe in Western Washington. But my question really doesn't relate to my job. I'm just wondering, how do we get the corporations that seem to be responsive to their shareholders to change the infrastructure plans? Because I think that's one of the biggest holdups, is they feel this duty to make the most money possible, or else they may find themselves replaced. And I don't know if you have had any, this is obviously an area you work in, so I wondered if you had any ideas about how to get corporations to address that.
Yeah, I think you've put your finger on, what economists call externalities, right? So these companies can dump CO2 into the atmosphere for free. And so the question is, how do you make them take on the cost of some technology that doesn't dump the CO2 into the atmosphere, that's going to cost more than just dumping that CO2? And so personally, I think that has to be kind of two approaches. One's a top-down and one's a bottom-up. The top-down is government. So government can do a lot to put a price on carbon and have the fact that the CO2 is going to the atmosphere no longer be free. These companies would have to pay something for that, and that's going to immediately make all the low-carbon energy technologies more competitive. The bottom-up side of that is that we could be doing a lot more in terms of R&D on low-carbon energy. So it's just a fact that we actually spend more on potato chips in this nation than energy R&D. So that's no exaggeration, and a lot of that R&D is actually going to fossil fuels, things like tar sands and oil shale. So we could be doing a lot more in our universities and in the funding that we get from places like the DOE to really push down the path of low-carbon technologies, and that will also help make those technologies more economically competitive.
If I understand my name is Larry Luton from Eastern Washington University. If I understand your existing commitments analysis, those are plants that are up and running. Have you or anybody else done an analysis on those that are in construction phase or that are in planning phase that doesn't look like they're going to turn around?
In fact, we have looked at that. So I use a data set that's a commercially available one by this company, Platts, that does energy analyses. And they have a great database of world power plants, and it includes some that are planned and under construction. The problem is the category that's planned and under construction is really big. And I think there's like this optimism that all these things are in the works. And so it's hard to really parse which of those is really on the books and going to happen and which of those are just in someone's mind. So if I included those in the analysis, you'd see a huge glut of these planned plants, and my suspicion is that's not real at this point. Not all of those are actually going to be built. So it's tricky.
We have one here. Go through here and then first and second.
Do I go first? Just an observation, and I guess you could comment on it. When you had the graphs that talked about the equity version, and just I've tried to ponder this and I'm Paul Pickett, but I'm speaking for myself right now. When you listen to what China says, they say, you guys in the West, in Europe and the US, have had a free ride. And so that purple is kind of what we've already cashed in.
Right.
And so it seems like from an analytical perspective, there's another level to this. And it's kind of something I've just pondered, and I think what you've done is fascinating because I've just kind of dabbled in the same question. A true per capita emissions would say something very different. If we said, let's have everybody on the planet get a certain allocation of emissions, then it might say, like, I just wonder what the answer would be if it means we really have to cut way back. We have to go for a massive decarbonization in order to give the developing world a fair shot at a per capita allocation of emissions globally. So I just think there's one more line there that you could add to that graph.
Yeah, so I sort of sped through that part, but if we did try to allocate the remaining quota per capita, we would actually see that current commitments, both in China and in the US, already exceed what we would need to reduce in order to hit a 2-degree target. So we would actually have to retire plants that are built and operating early in order to hit the 2-degree quota if we were sharing the rest of the pie among everyone on the planet equally. So that's obviously a pretty daunting thing. And that's really reflected in the idea that this RCP 2.6 is pretty far-fetched right now, unless we go and develop these technologies to have negative emissions, and we're stopping growth of fossil industry right now.
Hi, I'm Mike Solman. I'm a physician and I'm also with Citizens for Climate Lobby. The thing that I wanted to say, I was really glad you said what you said about if we started taxing carbon and getting rid of the negative externalities. Because I think the punchline for me is that this bit about 2.6 being implausible, certainly it's implausible with anything that's close to business as usual. But I think in the last week, Yale students, for example, just convinced their administration to invest their $15 billion endowment away from carbon polluters. The citizens can actually change business as usual, fee and dividend taxing carbon at the point it's extracted from the environment, giving the money back to households that are going to suffer from the pump cost, et cetera, are not business as usual, and in fact are unprecedented. And yet I think they're what are required for the implausible scenarios to become reality. Thank you.
Yeah, that's a totally fair point, and this is why it's so hard to assign probabilities to these different RCPs. It's because it's not even the case that it's a physical science issue of you can run an ensemble of models and figure it out. This actually has to do with people and their behavior and political will and economics fundamentally. So it's thought that we could solve the climate problem for 2 or 3% of the world's GDP, which is a pretty modest effect. That's roughly the same impact we saw from the global economic recession, and we've survived miraculously. So I think that it's something that could be done, and you make a fair point. When I say that RCP 2.6 is implausible, though, it's not just that I'm assuming we're going to continue on the business as usual. It means literally stopping building any new fossil fuel burning devices today. And to me, that's beyond not business as usual. That's an incredible order when you have billions of people around the world that are depending on having access to energy and are depending on fossil fuels for that energy. So it's more than just, you know, some political will in this country and getting people to buy a Prius. Like we've got an incredible hypothetical there to try and get at the 2.6 trajectory. So.
Hi, Linda Mertbout. I'm just a citizen here and a member of a lot of conservation groups. I'm just wondering if you could speak just a little bit on how important it could be for us as citizens here in the Pacific Northwest to really, really try to stop the coal and oil trains and the building of new refineries and ports.
Obviously, it's a huge hot topic with the terminals and things. I remember when I was here a few years ago even. You know, as I pointed out in that early slide, it's like the cookie jar. We have to leave these fossil fuels in the ground. So whether we're talking about the Keystone Pipeline or a new coal terminal in the Northwest, it seems foolish to invest in extracting and delivering those fossil fuels to consumers anywhere. We ought to be spending our dollars on figuring out how to compensate for intermittency of solar panels or wind turbines. And so as a citizen, as you asked the question, anything that you can do to speak out and say we shouldn't be allowing this, helping this in any way, I think that's an important thing. And all of these efforts could add up to something meaningful.
Hey, Steve, thank you. This is really interesting. It's Amy Snover. You made a really compelling point about the committed emissions over time and the implications for being able to meet or not meet 2.6. You also showed that we're on the barely above sort of the lowest scenario for increasing renewables. And I'm wondering if you could comment on the plausibility of those other scenarios for increasing our renewable portfolio, because it seems that's sort of the next step, right? If we could actually, which we can't, I agree on the implausibility, yep. But what is the alternative going to be? Have you taken a close look at the probable aspects of those scenarios?
I can speak to it generally. I think that that's something I'm actually most optimistic about in terms of our ability to grow the renewable energy supply. It seems like it's sort of this innovation problem that Americans in particular thrive on, this kind of issue, right? How we can build out these low carbon technologies. The problem is we have this entrenched fossil industry and we're fighting against it. And so the gas boom came up, and so this is one thing that I've done recently. We actually have an analysis going to be out soon that shows that just having cheap natural gas around isn't going to reduce our CO2 emissions, because that gas doesn't just compete against coal, it also competes against things like solar and wind. And so without some sort of a climate policy that's going to direct the benefits of that gas as opposed to coal and not compete with those better technologies like solar and wind, we end up about the same place in terms of our greenhouse gas emissions. So these are the kinds of things that if we want that renewable energy supply to grow and to get on one of those higher pathways, we need to be thinking about how to subsidize R&D of those technologies and try not to let the fossil fuels that we have compete with the rise of those renewable energies.